In this short video, I'll discuss the normality test. Here's the agenda. Topic number 1. Why a normal distribution important for finance? Topic number 2. For a normal distribution, we are going to enjoy its density function and the cumulative density function. Topic number 3. The procedure for such a normality test. Topic number 4. One typical example. Do IBM's returns follow a normal distribution? Topic number 1. Why a normal distribution important for finance? Actually, there are two reasons. Reason number 1, because a normal distribution or standard normal distribution have very good properties. A very simple distribution, two values, mean and standard deviation, could be used to determine the whole distribution. B, normal distribution usually is a base for other distributions. C, suppose we design a model, then we calculate error term. Error term is defined as the observed value minus our predicted value. So if our model is good, then its error term should follow a normal distribution with a mean 0. Reason number 2. Here, it is a very important assumption for finance. Stock return follow a normal distribution. Because of this assumption, we can use the Monte Carlo simulation to simulate stock price and return. Based on this kind of simulation, we can simulate Black-Scholes-Merton call and put options. Because Black-Scholes call closed form solution, we cannot use it to price Asia options. So we can simulate Asia options. Then, when we estimate value at risk, we can use Monte Carlo simulation. This is topic number 2. We are going to use Excel to draw density, standard normal density distribution, and cumulative standard normal distribution. So first one, we enter X value. Let's use -3 up to +3. So we're going to use 0.25 as our incremental value. Okay, so let's copy and paste. Okay, so then the first one is density. Okay, the density function we use norm standard. S stands for standard, DIST. And the first input value is X, the second one whether it's cumulative or not. So we enter X. Okay, we are going to draw the density function, so it's false. Then we copy and paste. We highlight both columns, we click data, we click insert, we click recommended. So this is graph. This is for the density function graph. Okay. The next one, we are going to calculate cumulative. We apply exact same function, norm.s.dist. So this time we enter choose. Cumulative, we enter choose. And we copy and paste. Okay. To draw the graph, we highlight X column, hold Control key, then we click insert, recommended. So this is our cumulative density function. Okay, we put them together. Okay. On top is our density function, bottom is cumulative. Because it is standard normal, the mean is 0, standard deviation is 1. So this is mean is 0. Okay, this standard deviation equals 1. And this is symmetrical. On the left hand side, we are going to have 50%. On the right hand side, we have 50%. This means if we draw a random number from standard normal distribution, we have 50% chance this random number less than 0, and 50% chance is above 0. The 0, the cumulative is 0.5, it's 50%. Okay. So let's look at these two values. Okay. So if we ask what is the probability? What is the probability between negative 2.5 and negative 2.25? Okay. So actually the probability between these two values is the difference between these two. So actually equals 1.22% minus this one. So actually this is a probability we are going to see between these two values, negative 2.5 and negative 2.25. Here's a procedure for a normality test. Our hypothesis is IBM return follow a normal distribution. So after we download the data and retrieve to our Excel, step number 1, estimate return and their mean and standard deviation. Step number 2, generate the adjusted return by using equation number 1, where mean and standard deviation are from step 1. Step 3, generate a bin column from negative 3 to positive 3 with an incremental value of 0.25. Step 4, generate a column for the frequency for our data. Click Data, Data Analysis, then Histogram. Input our adjust return and the bin columns. Step 5, generate a column for the frequency based on the standard normal distribution by using equation number 2. The number count for each bin equals probability based on the standard normal distribution times n. Here n is number of total observation. Pi, we apply norm.s.dist. So this is cumulative standard normal distribution. The difference will be probability inside this specific bin. Step 6, estimate deviation using equation 4. Last step is the summation of this error term will be our test statistic. Then we compare this sum with a critical value. If it's higher than critical value, we reject null hypothesis. To calculate a critical value, we use the related Excel function called CHISQ.inv.rt. Please pause this video to download or retrieve data. There are 4 methods to get the data. Method number 1, you can go to Yahoo Finance to download 10 years IBM's monthly historic price data. Method number 2, if you are taking my course right now, just type 2 lines. Method number 3, if you know R, you can issue following 1-line R code. Then you go back to method number 2. Method number 4, you can simply download a CSV file as the following link. To get the data, let's try method 2. Okay. Launch R, then type source http data yyyy.com get data capital R. Okay. R is case sensitive. Pay attention to your spelling. Hit enter. Okay. So show IBM monthly. Okay. Type show IBM monthly. We enter 0. Okay, then we are going to use cut data. Suppose we use 10 years data. Cut data. So this 2010, 2019. Then we go to Excel to paste it there. Now we have the data. Let's conduct the test. Okay. The first step is estimate return and their mean and standard deviation. Okay, so let's call it return here. Return will be the closing price this month divided by adjusted closing price previous month and -1. We copy and paste. Then we calculate mean and standard deviation. So we calculate mean and standard deviation. So mean will be average of H columns. We copy and paste. Then we replace average with standard deviation. Just double check. So this is average H column. This is STDV with H column. So this is mean. I'll return this standard deviation. Then we apply equation number 1 to calculate adjusted return. So this is adjusted return. Okay. Adjusted return will be our return minus mean. Hit F4 to lock it. Divide by standard deviation. Again, hit F4 to lock it. And then we copy and paste. So this is adjust return column we are going to use. Step number 3, we generate bin from -3 to +3 with an incremental value of 0.25. So let's call it bin. So it's -3 equals -3 plus 0.25. So let's copy and paste. Okay. So as we only nice, it's okay. We add a little more. Okay. Okay. Step 4, we generate column and call the frequency for our data. So data analysis histogram. So we click data analysis. We choose histogram. So the first column will be our adjust return column. Okay, Control Shift down. Okay, second one will be our bin. Okay, so this is bin going down. Okay, because we have to check the label, I include the label. So this is our output range. So let's put here side by side. Then we click OK. So this is our frequency. So this is frequency for our data. Okay. So next one, I'm going to generate a frequency for normal, for standard normal. Okay. And so based on this one, so you see this one generally calling for frequency. So this is probability times n. So this is total observation. So let's count. So this is n. And so let's count. It's summation. How many frequency we observed. Okay, so this is, so we have 119. Okay, so let's calculate this probability first. Otherwise, this is too complex. So this is P, probability between the bin. So let's use this one. Okay, so the probability between this value and this value I mentioned here is use norm dot s dot dist xi 2 minus x minus 1. So this is equals norm s dot dist. So this is this value minus, sorry, so this is 2 minus norm s dist. And for the previous one, so this is -3, then enter 2, because we use cumulative. So this is cumulative. I repeat. Okay, so this is probability between this bin. Okay, so actually we use norm dot s dot dist, so this value, minus norm dot s dist k5, the previous one, and 2, both are true. So this is probability. Then we copy and paste up to here. Okay, and for the first one, so let's copy paste, and we are going to see an error message because this is not a number, right? This is not a number, so we can manually enter. So this is -3. We can manually enter -3.25. Okay. 3.25 we enter. So we have the probability. Okay. So this is again the probability times total. So this is according to equation number 2. So this is the frequency based on the normality assumption. So this is equal probability times number of observation. Again, hit F4 to fix it. So this is our count based on the normality assumption. Okay, so this is our error term. Okay, this is our error term. Okay, so error term will be the frequency based on our data. So I'm going to use red one. So this is use purple. Okay, purple. Okay, to calculate the chi-square critical value, we need two numbers. One is alpha. So let's assume is 5%. The second value, a degree of freedom. So let's count how many bin we have. Okay, so this is the bin. The critical value, so this is our chi-square critical value. Excel file uses CHISQ-INV right tail. So this is our probability 5%. The degree of freedom is n. For the last step, step 7, the summation of all the above error term actually is this column. O column will be our chi-square test statistics. So let's type sum is equal sum all this value so this value will be our test statistics. Okay, we're going to compare it with a critical value, chi-square critical value. To calculate the chi-square critical value, we need two numbers. One is alpha. So let's assume it's 5%. The second value, a degree of freedom. So let's count how many bin we have. Okay, so this is the bin. The critical value, so let's see, this is our chi-square critical value. Excel file uses CHISQINV right tail. So this is our probability 5%. The degree of freedom is n minus 1. Okay, so the critical value is 38.88. Our test statistic is 35.35. So this is our decision. Okay, so this is our decision. So our decision is if our test statistics is higher than critical value, then we reject. Otherwise, we accept or fail to reject. Okay. Then, because 35 is less than 39, we accept the null hypothesis. Okay. So if we change this one to 1%, so this critical value jump to 45.64%.